Hello and welcome to today's Environment and Energy Leader webinar sponsored by Montrose Environmental Group, an environmental services company. My name is Jessica Hunt, and on behalf of the entire team at E&E Leader, I welcome you to this wonderful panel of experts that we have today. The title of today's presentation is a Q&A panel on the proposed PFAS drinking water MCLs and what these limits may mean to your challenges with PFAS. I know everyone is extremely excited to hear from our presenters today, but I do want to go over a few technical aspects of the event before I hand it over to the presenters. Any questions specific to the presentation or technical issues, please feel free to submit those using the Q&A widget, which is already open for you on your screen. I just ask that before you send a message that you utilize the help widget at the bottom of your console to troubleshoot on your own before sending a message to our team. During today's event, you also have the opportunity to speak with other attendees using the attendee chat widget. So jump on, tell us where you're joining from. I know we have quite a lot of countries represented from our registrant list. So it will be great to see where people are joining us from today. And then obviously we are going to be answering a lot of questions today during the event. Please continue to submit questions for all presenters while they are speaking. If we don't get a chance to answer your specific question during the event, don't worry, because a member of Montrose's team or one of the other subsidiaries will follow up with you as soon as they can. And at this point, I am going to hand the presentation over to Martha, and she's going to run the show from here on out. So again, thank you on behalf of E&A Leader and Montrose for being with us today.
Welcome, everyone. Thanks for joining us today for our question and answer panel on the proposed MCLs. My name is Martha Maier. I am the PFAS program leader for Montrose, and I'm acting as the moderator today. And we have a great group of PFAS experts from Montrose and covering all disciplines from toxicology, analytical, remediation, and water treatment. So we'll get some really solid answers to everyone's questions. We're going to start with some quick introductions and then move into the MCLs and then go back and have give a timeline. How did we get here? So we're going to go back all the way to the year 2000 and see how we arrived at these numbers. And then after that, we'll go ahead and get into our questions. Next slide, please. As I've said, my name's Martha Maier. I have been involved in the PFAS space for well over 10 years now, primarily on the analytical end. I was the former director and owner of Vista Analytical Laboratory, who has been involved in PFAS analysis since 2007. We became part of the Enthalpy family a couple of years ago, and which is under the Montrose umbrella. And I will hand it over to you, Rock.
Good day, everyone. Thank you, Martha. My name is Rock Vitale. I'm the Technical Director of Chemistry and the Managing Principal of Environmental Standards. Environmental Standards has had the privilege of becoming a Montrose company a little over a year ago. And similar to Martha, my company does quite a bit of chemistry consultation, and we've been working in the fluorochemistry project space for about 2 decades. So I'll pass it to David next.
Thanks, Rock. My name's Dave Campisti. I work in the research and development area of ECT2. I'm located in Colorado Springs, Colorado, but our research and development area is in the Research Triangle Park of North Carolina. I work across a variety of different disciplines and areas, including carbon capture storage, microplastics, waste to energy, but of course, PFAS is at the top of that list as well. So in the PFAS space, I work on optimizing ways to remove PFAS from the environment, oftentimes with regenerable resin, optimizing that process, but also with single-use resin or single-use media or other technologies as applicable. So I'm also involved in technologies that focus on the destruction of PFAS compounds. I've also had the honor of editing two books on PFAS, which has provided me with a broad understanding and exposure to the challenges of dealing with PFAS, including toxicology, which is, of course, emerging, policy and regulation, which is what we're here to talk about today and being updated all the time, analytical detection, new methodologies, lower limits of detection, and remediation technologies, better ways to treat PFAS, destructive ways to treat PFAS. So, all these areas, toxicology, analysis, the policy, the remediation technologies, they're all changing, all affecting one another. And as I think we all know on this call, this makes PFAS a very dynamic area of focus. So excited about the call, excited to be here, and thanks for attending. So now I'll turn it over to Tiffany Kornberg.
Hi, I'm Dr. Tiffany Kornberg. I'm a toxicologist with CTEH, and I work out of the Portland office with Dr. Angie Perez, who some of you may be familiar with. In the Portland office, we focus on PFAS as it's related to regulatory guidelines in toxic tort litigation. We've been involved in several cases where there's an alleged exposure and then subsequent health effects, and are also involved in responding and critiquing these ever-changing regulatory guidelines. And I will pass it off to Stephen.
Yes, good morning. Thanks for attending. I'm Steve Koenigsberg, Senior Principal in the Montrose corporate structure. I sit in Irvine, California. Got about 30 years in the environmental business. As a soundbite, I'm a subject matter expert in site investigation and remediation, a focus on advanced processes in that regard. I've been a product developer and a consultant. Like with many of my colleagues at Montrose, we're far more than are represented here. We're close to 3,000 strong. It's not unusual to interact with people with at least a decade of activity in all things PFAS, which coincides with the emergence of PFAS. The emerging contaminant emerged before a decade ago, but it kind of entered into a high profile about a decade ago, and that's where many of us have made our mark. Thank you for attending.
And here we have the proposed MCLs and hazard index. So PFOA and PFAS, very straightforward. The proposed MCLs are set at 4 parts per trillion each. A little bit different for the 4 additional PFAS that are being proposed for regulation: PFNA, PFHXS, PFBS, HFPODA, commonly known as the Gen X chemicals. They will all be regulated as a group if this proposal goes through as suggested. We have the hazard index equation below, and basically each of the concentrations will be plugged in, and then the hazard index must be, the limit will be 1. So we'll go into this one a little bit later. Next slide, please. Thank you. And now, how did we get here? And we're going to go back to 2000 here, when the EPA first called for a phase out of PFAS. And this happened over the next 2 years and ended in 2002. After that, EPA created a stewardship program for PFOA, and where they worked with different manufacturers to reduce the use and manufacturing of PFOA by 95% by 2010, with a goal of 100% by 2015. So in the meantime, EPA published provisional health advisories. So these we'll be talking about a little bit later, but basically the health advisory is the level under which EPA anticipates that there won't be any human health effects. So PFOA was first set at 400 parts per trillion and PFAS at 200 parts per trillion. That same year, EPA published our first validated analytical method for PFAS, for analyzing for PFAS, and this is EPA method 537. This is a drinking water method, and it was used then sequentially in 2012 in the unregulated contaminant monitoring rule, UCMR 3. So this was a study, a survey of drinking water levels of PFAS, including PFAS, all around the United States. I also want to mention that same year that one of the studies that's used extensively by EPA for the research to set the health advisories and therefore the MCLs was also published that year on the work in the Faroe Islands. And Tiffany will be talking about that a little bit later. So 4 years after that, EPA published lifetime health advisories for PFOA and PFAS at 70 parts per trillion, both individually and combined with a limit of 70. And then things really got going in 2021. This is when EPA announced their determination to regulate both PFOA and PFAS, and also released their PFAS strategic roadmap, which outlined their plans for PFAS and also a timeline for which these would occur up through 2024. Last year, of course, EPA issued interim health advisories, PFOA now at 0.004 part per trillion and PFAS at 0.2 part per trillion. These are interim levels, and they'll be valid through the promulgation of this Safe Drinking Water Act regulation. At the same time, final HAs were issued for Gen X at 10 parts per trillion and PFBS at 2,000. And you'll notice on the hazard index, the limit for each of these compounds is the one that has been added into that hazard index equation. Then, of course, last month, the proposed MCLs were published in the Federal Register, and that brings us right here to today. Upcoming, we have May 4th, a public hearing on the proposed regulation, and then comments. I think there are over 2,500 comments already that have been received. This comment period will go through May 30th. EPA anticipates promulgating this regulation by the end of this year, and then from that date, compliance will be required 3 years from that date. So there's a lot to do in those 3 years, so we will get right to our questions. So our first one is for Tiffany. What are the drivers for the 4 part per trillion MCLs for PFOA and PFAS?
Yeah, thank you for that question. So for PFAS and PFOA, these proposed MCLs were based on the idea that these values were as close as feasible to the MCLGs, which are maximum contaminant level goals, also proposed by EPA in this document. So the MCLGs for PFAS and PFOA were set at 0 because the EPA classified them as likely to be carcinogenic to humans. For PFOA, this is not necessarily a surprise. There are 3 key human studies the EPA used that show renal cell carcinoma or kidney cancer in select populations. And I won't go into all of the details on these papers. I will just say there are some key methodological flaws. One is that all 3 of them used a highly biased population in their study. For PFAS, which was classified in this MCL proposal as likely to be carcinogenic to humans, the EPA acknowledged they had mixed results for humans and results were overall inconclusive. Instead, they relied on a bioassay, chronic bioassay done in rats by Butenhoff. And again, I won't delve into the specifics, but needless to say, there were some critical methodological flaws and then also some analytical issues as well. Regardless, the EPA used these papers to reclassify both PFAS and PFOA, and then to subsequently set these MCLGs at 0. So they use these MCLGs in conjunction with a minimum quantitation level for analytics that they believe can be achieved at 75% or more of laboratories using their specific method. So that is how we got to this MCL of 4 parts per trillion for PFAS and PFOA. Next slide.
Steve, this next one's for you. How pervasive are PFAS in drinking water in the United States?
Okay, well, there are a number of publications. I think we'll see a lot more over time. A group at Northeastern University, working with colleagues, essentially put together a working group. Many people have seen this map with numerous dots on it where things are occurring at military bases and landfills and so forth. It's called a presumptive contamination number based on what are likely sources. Again, industrial facilities, from manufacturing processes, the AFFF, which is the firefighting foam, which is one of the prominent insults to the environment. Military, of course, in a firefighting mode, airports, landfills, leachate. So they looked at all the possibilities, and you have 57,412 in the moment. I think we need something like the national debt clock in Times Square, because that number is going to change frequently. Going back to something that is more digestible, similar studies essentially put the number at about 1,750 as the number of sites that we would call well characterized to different degrees. And some people advocate putting another 1,000 or so on top of that, where there's kind of a whiff of the fact that these could be major issues, like one hit and one well, as some people describe that next level. So that's quite a spread. One other quick comment is there's a study where they looked at drinking water systems, and reasonably low number, 11% in an Illinois study, 14% in California, in sampling wells in drinking water context. Those are the percentages that reveal some level of PFAS, an actionable level of PFAS. So that would be the prevalence of the PFAS problem as we understand it today. Thank you.
Thanks, Steve. And that really fits well with what is in the promulgation, or the proposal, that EPA expects about 21% of the facilities to have levels above the trigger level. So that's under the MCLs, but that kind of all fits with the different state percentages you were bringing up. So on to our next question. Rock, there are 3 PFAS drinking water methods available on the website. So which one should be requested?
Thank you, Martha. So as we saw in our timeline, the original publish of method 537 was back in 2009. It is a drinking water method, which means laboratories are not allowed to digress or preform. They are really supposed to follow it as it's written prescriptively. Then in 2018, out came method 537.1, which was a revision. And frankly, the only thing that was different in 537.1 was the addition of 4 smaller carbon PFAS compounds. In May 2022, EPA published method 533 for PFAS, which was the first drinking water method that actually had and stipulated the use of isotope dilution, which, if you're a chemist, is pretty much the gold standard as it relates to quantitating whatever analytes you're interested in. Currently, for the looking at MCLs and complying with MCLs, you would use method 537.1 or method 533. And I'll caution, because the analyte lists between those methods are different. So you really need to check which analyte list will prevail in terms of your requirements. And unfortunately, potentially, you may wind up doing both methods, or asking a laboratory to tack on compounds on one or the other. Unfortunately, then you get into issues of compliance. So 537.1 or 533 are the 2 methods to be requested. Next slide, please.
Thank you, Rock. Dave, can the market support that many drinking water treatment systems getting built at once?
Good question, Martha. Thanks. Yeah, it's certainly going to put a stress on the manufacturing and fabrication sectors, but at the same time, it goes back to kind of the timelines that you shared on your initial slide there, with the promulgation of the MCLs going forward. So if final promulgation occurs by the end of 2023, that's when that 3-year window for entities to gain compliance will begin. And so it's during this time that your affected organization should be developing a procurement strategy acquiring or going after grants and the use of state drinking water revolving funds, which have recently been plussed up with the bipartisan infrastructure law and the Inflation Reduction Act. There's a lot of money in there for PFAS treatment. But this is when you interface with your regulators as well, talk about site modifications and prep and the lead times associated with getting drinking water treatment systems ordered, manufactured, and procured. So, I think the sector will be able to handle this. Demand will increase, the market will respond, but of course, that's not without increasing costs that will be expected. Next question.
Sounds like it's a good plan then to at least start early and see where you are and whether those treatment systems are going to be needed. Tiffany, next question. What is a hazard quotient and why was it selected for risk screening of PFNA, PFHXS, PFBS, and Gen X?
Right, and so you can see we have our equation up on the screen here. A hazard quotient is basically calculated for a particular chemical where you would take an exposure metric, such as the concentration in drinking water, divided by some health reference value for that chemical. So for a mixture of chemicals, for example, the 4 PFAS compounds in particular, we would calculate this hazard quotient for each individual compound and add them together to create a hazard index, which is a very common approach for risk management of mixtures of chemicals. So the EPA is using the hazard index to estimate potential aggregate health hazards associated with various chemical mixtures, such as these 4 PFAS compounds. Next slide, please.
And I just want to take the time out to thank everyone who did send these. These are questions that we received in advance, and we're still receiving them, and we'll add those at the end. Rock, so our next question is, how will the trigger levels affect monitoring requirements?
There are a number of actually questions streaming in about low limits of detection and can we really see that low, and I'm paraphrasing a bit, but trigger levels of 1.3 parts per trillion. For those who've been in the environmental field for a long time, you know the proverbial J values and what they are. J values are concentrations that are reported by laboratories that are below the lowest calibration point. For PFAS, 537.1, 533, the lowest calibration point can vary somewhat by laboratories they're using. I think the quote was 75% EPA said of the laboratories can meet an LOQ of 4 parts per trillion, which may be true, but if you're looking at 1.3 part per trillion as a trigger level, not too many laboratories are calibrating down at 1 part per trillion as their lowest calibration standards. That may change because of this demand, but at the moment, if you have a detection of 1.3 for any of the MCL compounds plus the equation, you are down in the area of estimated concentrations. Obviously, not a good position to be in from a compliance standpoint, staring at a J value estimate. So next slide, please.
Thank you, Rock. We have another one for you here. Do you have any suggestions for processing PFAS results when reported below the PQL of 4 parts per trillion? And how to identify estimated values at or above the 1.3 part per trillion trigger level? So related.
So directly related. So I think one of the things that is extremely important is to plan with the laboratory that you're contracting. If the laboratory can achieve their low calibration point at 1 part per billion, 1 part per trillion, obviously anything at or above that level can be considered quantitative. It is pushing the technology. It's not a comfortable position to be reacting to a compliance issue based on estimated data. The technology of triple quad is absolutely amazing. We can see down to single digits. The word I used is see. We can actually see and qualitatively identify. Quantitation down to these low part per trillion levels is extremely difficult. Not a good situation to be reacting to or having to do something different from a compliance standpoint based on an estimated concentration. I wish I had a magic wand, but I don't. Next slide, please.
Thank you, Rock. Tiffany, how will the MCLs change as additional PFAS are regulated?
Yeah, great question. So as it is now, PFAS and PFOA have separate MCLs, while the Gen X chemicals, PFHXS, PFNA, and PFBS have this combined hazard index. So I would expect that as this research develops on these other types of PFAS compounds, we would see more of them added to this list. And this is already happening. In February of this year, Canada released proposed guidelines related to PFAS, where they discussed that the sum of total PFAS should be used to compare to the screening value. And in Canada, they listed 30 different PFAS compounds. So my prediction would be that the EPA will modify their MCL to be based on a sum of total PFAS, and likely, again, using this hazard quotient risk screening method, which we talked about earlier. Next slide.
So how is it determined whether a facility is in compliance? And I will take this one here. We're going to concentrate right away on this initial 12-month monitoring period. So this will be the initial compliance. And basically, a facility has to have 1 year's worth of data, which is the data are going to be averaged. So for most facilities, it's going to be quarterly. It does depend on the water source and then also the size of the facility. So we keep that running total going, averaged. If an analyte is detected less than the quantitation limit, that practical quantitation limit, it's going to go in as a 0. So that's averaged, and then that will determine whether it's above or below both the MCLs or the hazard index. And this all needs to be done before the compliance level, so within this 3-year period. Now, they do make allowances that it's possible to use UCMR 5 data. So that is starting this year. It's a new survey of PFAS at facilities all around the United States. And that data can be used to determine the initial compliance. And also there are allowances for states, state monitoring programs, as long as they meet the criteria, 1 per quarter, et cetera, that they can be used also. So one thing I just want to point out is there's nothing out of compliance until you have a year's worth of data, unless one sample for an analyte is high enough that even if you had zeros for the rest of the year, you're still out of compliance. So at that point, then a facility would be out immediately. So next slide, please. And back to Rock. Can accredited laboratories really accurately see down that low for these PFAS levels in field samples?
Well, there's a loaded question because field samples can imply quite a few different things. Can imply groundwater that may be used for potable purposes after treatment. It could imply discharge, and so on and so forth. The more complex the sample matrix is, the harder it is to confidently be looking down that low in a single part per trillion levels. If we are talking about clean drinking water samples to be used for drinking water purposes, laboratories can see, most laboratories can identify and quantitate pretty well down to 4. And a lot of the work that my team looks at for looking at groundwater projects all over the country that are using drinking water methods, some laboratories are at 2 parts per billion as their low standard, 3, 4, and up to 5 part per trillion as their low calibration standard. So it is important, and I'm going to come back to what I said before, is understanding how low can your laboratory report down to what is their lowest calibration point. There's a lot of questions about uncertainty, and no matter which way you slice or dice it, when you're down into these low part per trillion levels, even using drinking water methods, there's a fair amount of flutter going on. But The LOQ has to dictate, and hopefully your lab can do at or a little better than 4 parts per trillion. Next slide, please.
And as you touched on, Rock, this isn't something that is very obvious by just using an accredited laboratory, because you don't need to be accredited that far under the PQL. So that's something that people are going to really have to look at when they're talking to their labs. Our next question's for Dave. Are there effective treatment options that can obtain these levels, and what are they?
Thanks, Martha. Yes, there are effective treatment options that can obtain these levels. So seen on this slide are 3 different conventional and widely accepted technologies that have the demonstrated ability to remove PFAS to these low levels. The first is GAC, or granular activated carbon. This stuff has been used forever to remove contaminants. Maybe not forever, but there's like Sanskrit text from 2000 BC that I always like to quote. It says, you should store your water in copper vessels, expose it to sunlight, and filter it through charcoal, the predecessor to activated carbon. So operators know how to use it. Regulators are very familiar with it. The contaminants, in this case PFAS, are hydrophobic, and they prefer the granular activated carbon matrix to the water matrix, and they are removed from the water. Now, there is a limit to the capacity of the carbon for this contaminant, and then that will have to be changed out once that capacity is reached. The second on this slide is ion exchange resin. This uses 2 mechanisms for removal. It's the same hydrophobic absorption mechanism like the granular activated carbon, but it also, the resin has a selectivity for certain charged ionic species like PFAS over other charged species, and there's an exchange of ions, hence the name, ion exchange. The PFAS goes from the plastic, goes into the plastic resin bead and attaches there, and the counter ion, for instance, chloride, is exchanged and goes into the water phase. So although the capacity for ion exchange, same comment here, is generally higher than granular activated carbon, there's still a capacity or a limit to how much this resin can uptake from the water source. So once those capacities are reached, either for the GAC or the resin, new media needs to be procured and changed out. So the old media needs to be handled and disposed of, or incinerated, disposed of in a landfill or incinerated. Then regarding membranes, the third one on here, these use size exclusion or selective diffusion mechanisms to reject PFAS from passing through with clean water. So while these technologies have shown to be effective at removing PFAS at low concentrations, they do produce a concentrated brine that has to be dealt with. Could be 10%, could be up to 20% of the volume of water treated. So this will then require further treatment. Oftentimes that's with granular activated carbon or resin. Another option to get rid of this brine might be deep well injection. Generally, I'll say the cost of membranes for large-scale drinking water applications is generally higher than granular activated carbon and the ion exchange options. And yeah, as just an add-on here, there are emerging technologies such as novel sorbent media and other concentrating technologies such as foam fractionation. These have shown promising results, but oftentimes they encounter challenges when they're employed at full scale, especially the scale you're talking about for a lot of drinking water treatment facilities. So the cost, the scale, the potential regulator certification issues have to be dealt with. And so those are just things to look at when you move away from these 3 conventional treatment technologies. But yes, they can achieve the low MCLs that we're talking about here today. Next slide.
Thanks, Dave. Some good information there. And we're going to follow up right away with another one. Where's all that waste headed?
Yes, so another good question. That is one of the knocks on these 3 core technologies. You really just transfer the contaminants or the PFAS from one matrix to the other, to another. So from the water to an adsorbent media, the GAC or the resin, or from the water to a concentrated brine, and you have to handle that. So once the media of the capacity has been reached, it needs to be disposed of. This can be done through a landfill, putting that into a landfill, but now you've got considerations with landfill leachate being generated and future treatment that might need to be incurred there, or with the proposed CERCLA designation as a hazardous substance, whether or not you've got to With strict liability, we'll be responsible for that with future liability. So that's a concern. Or things could be incinerated, generally higher cost. There are some issues associated with incineration and understanding if you're getting full mineralization or destruction from incineration. The state of the science is still out on that. You also have reactivation options for granular activated carbon. So that does get a little tricky with potable grade granular activated carbon. The reactivation is conducted in a custom fashion, custom reactivation as opposed to like a pooled reactivation. And it's also conducted in a dedicated NSF 61 certified facility. So you have to think through those intangibles. For resin, there is a regenerable resin option. This too is also a little bit tricky for potable applications because of the use of solvent in the regeneration process. This has to be dealt with from a regulatory approval standpoint. So potable applications are generally low concentrations that we're trying to remove, where single-use resin can often last for many months, like more than 12 or quite some extended period. Where the regen should really be strongly considered is when treating higher concentrations where you're having frequent changeouts that are anticipated, and then you'll start to see some significant economic gains when you do the regeneration process. Next question.
Thank you, Dave. Will the EPA be adopting a draft 1633 or the final version of the method to address a longer list of PFAS in drinking water? And we just have been getting more questions in the chat on that too. So I think this is a good one for you, Rock.
Well, thank you. First of all, it's important to realize that 1633 is not a draft method. It has not gone through any draft or final rulemaking whatsoever. It was a method that was posted on EPA's website, and they threw it out there and said, let us know what you think. My team provided 2 rounds of comments, and it still has not undergone draft rulemaking. Unfortunately, agencies like DOD are accrediting labs to the method, and we're seeing NIPTES permits that actually are referencing it now. So we sort of had it jammed down our throat, like it or not. The issue with 1633 is it is not a drinking water method. It is a catch-all method for surface water, groundwater, wastewater, solids, biosolids, tissue. It's a catch-all method. It's a pretty good effort, but there's a lot of changes, and we've had 2 rounds of comments, as I mentioned, before it could be ready for prime time. The interesting part about 1633 is that there are PFAS compounds on there that are sort of undergoing the dress rehearsal, as it were. With enough laboratories using 1633, we can gather a lot of performance data on the additional compounds, which may at some point be added to the drinking water list through the UCMR process. So it is a decent catch-all method, but it is not a drinking water method. And unfortunately, it's not even a draft method yet through the Federal Register. Next question, please.
And another one for you, Rock. Testing for fluorine seems to be a way to screen for the presence of PFAS. Is there a protocol or some best practices used to communicate the rationale, limitations, and uncertainties around what results may or may not suggest?
First of all, for drinking water, there is a total organic fluorine method, and again, similar to 1633, out came method 1631. Did not go through rulemaking. It was posted on EPA's website, and they said, hey, let us know what you think. So again, we had a number of comments issued directly to the agency for method 1621. Total organic fluorine, because the idea is organic fluorine is man-made. There's no such thing as naturally occurring organic fluorine. So if you can measure organic fluorine, that means it's man-made. Unfortunately, organic fluorine is being used as a proxy for total PFAS because there's thousands and thousands of individual PFAS compounds. The idea is, and for some of the older environmental professionals, we used to use 413 and 418 for total petroleum hydrocarbons. This is akin to that. It is a total organic fluorine, which is sort of giving you a total PFAS number if you want to consider a worst case situation. So things like solids, things like wastewater, things like a variety of different things. Now, we can't see down to 4 parts per trillion or down to part per trillion at all using method 1621. So while the idea is there for very high concentration groundwater, where you've got lots of PFAS, it's a relatively inexpensive, in little quotes, because the quote I heard was $600 a sample for 1621. It's a way of screening samples that you are pretty sure have high levels of PFAS. It has no application for drinking water down to 4 parts per trillion. Next slide, please.
Dave, what are the projected costs if the regulation is promulgated as written?
Yeah, that's difficult to say for, an individual municipality, as there are a lot of variables to consider in that, right? The volume that you're treating, or the flow rate, the initial PFAS concentrations, what the target objective is, other constituents in the water that can affect breakthrough, the waste transportation, the waste disposal costs, the transportation costs also have to be considered. So that's difficult for an individual municipality, but from a more holistic answer, the EPA did quote some numbers for expected costs of treatment. The EPA cited, there's approximately 66,000 community water services in the states, with 3,400 to 6,300 anticipating a need of water treatment or finding another water source. And the annual estimated cost from the EPA to procure treatment for these affected facilities is between $772 million to $1.2 billion per year. These numbers could, of course, go up if water systems are required to dispose of the PFAS as a hazardous waste, and Department of Transportation considerations come in with managing a hazardous substance. But they justify this with an expected cost avoidance of numbers greater than that, 1.23, slightly greater than that billion in savings by avoided disease-adjusted life years. So the health effects the savings will be greater than the cost of implementing this treatment. Next question, Martha.
Thanks, Dave. Steve, what consideration do the proposed MCLs make for the question of PFAS concentrations that exist as background environmental levels?
Okay, well, this fits into what I would call a meme that's been circulating, not as prevalent as the forever chemical tag that we see in the media, but people are saying it rains PFAS, okay? And I know how this got started. There are some industry groups, casual conversations that start showing up in presentations people make at conferences. The truth of that is different than what it appears to be. There are some publications in this space. There are more coming. And, essentially, some of the phraseology is kind of the tagline is atmospheric transport and wet deposition. And some of us know, you find it in the Arctic, Antarctic, remote areas. So we do have a worldwide distribution of PFAS. The question is, how does it get there? And is it about atmospheric transport and wet deposition? The fact is that we're still learning about this. The dynamics of the deposition has a temporal and spatial variability. There are some statistics. If you do a rainwater study, you'll see numbers like 20% of the samples, producing an average of, say, 10 parts per trillion. But what really matters is, how does this affect your operations in compliance? So I think the obvious answer is, if there's background, you measure it, and that is part of the ongoing process to comply. So if you have sites with PFAS releases, the background becomes a de facto cleanup goal. In the mix, of course, we haven't seen it yet, but there will be protocols, not just established, that have to be adhered to in order to get through the process. One unfortunate thing is, especially in the drinking water requirements, if there is background, you got to take care of it. Doesn't matter how it got there. The drinking water suppliers will have to deal with what exists plus the layers on top of the background. So yeah, you can say it's raining PFAS, but you have to be cautious and parse out the truth from the generalization. Thank you. Next slide.
Thanks, Steve. Are there any special sampling precautions that are needed to avoid contaminating samples? After what we just heard about background, it's very relevant.
So yes, there are. In drinking water, obviously, if we're talking about monitoring MCLs down to 4 parts per trillion, the fact of the matter is PFAS has been around for a very, very long time. Everywhere we look, including, as Steve just described, rainwater, we have detections. So special precautions, clean rooms, sort of the approach to collecting samples, removing screens, collecting the sample directly into the sample bottle, collecting a series of blanks. Cannot overemphasize the need to collect a series of blanks with your samples to be able to assess, is there any background contribution from the bottleware, the reagents, the handling, etc. So yes, these, no pun intended, it has to be treated like with kid gloves. Next slide, please.
Thanks, Rock. And Steve, what do you anticipate are the most significant areas that would generate pushback in this proposal?
Well, it's a very interesting phenomenon. First of all, the answer is simply the significant area is these extremely low concentrations for compliance that are difficult to measure from everything Rock and others have shared this morning. The thing I observe is that it's a function of kind of a social statement with social media and so much instantaneous communication. It creates a groundswell where people can really get in there, with their interests, industries. I've seen stuff on LinkedIn, chemical organization put out about 100 letters from their membership saying, it's the end of Western civilization as I know it here because I'll be out of business. I can't deliver my product or service. Unfortunately, and I've done some investigation on this, don't shoot the messenger, but the fact is that in any movement of the needle is unlikely. And why is that? Well, we may have a little bit of a bias trying to protect our clients and trying to do things, quote unquote, more reasonably. But the fact is that the EPA has a mandate to protect the public. So there are two sides to the equation. And so while industries, water purveyors, and so forth are trying to push back on things that will damage their interest, the EPA has this mandate. And even if there's a groundswell of protest on the business side, and if you speculate politics could enter the fray, talk to your congressperson, have hearings. The sad fact is that the legislative branch cannot dictate policy to the EPA. So they rule. Now, there have been some rare cases of reversals in the EPA, but there aren't many of them. And so I think we're looking, we'll see what happens. But this is such a different, high-profile, never-before-seen circumstance. Something different could emerge. But I don't have a crystal ball, but it's going to be, let's say, very interesting to see how this process sorts out by end of May and then what happens after that. Next slide.
Thanks, Steve. Dave, what cleanup methods exist to remove PFAS contamination in the soil that leaches into the drinking water sources?
Right. Thanks, Martha. And, first off is a risk-based corrective action and to see how much PFAS is leaching into the groundwater or the water that's being used as a source of drinking water. If it's isolated and not affecting drinking water, then you need to consider that. You don't need to dig up every molecule of PFAS. However, this question says that it is leaching into the drinking water, needs to be remedied, and so You could see an excavation procedure that could be possible. That would be costly. However, it is done, often done. And there are other thermal technologies that can be used to remediate impacted soil, generally higher in cost than maybe a soil washing solution, which isn't entirely easy by itself either, because certain components or fragments of the soil contain more PFAS or are harder to remediate. For instance, soils that are high in organics or that contain a lot of fines, those are more difficult. So you might want to segregate those soils, and those soils would go to a landfill, whereas you could wash with a cleaning solution the other material and then be able to reuse that and remove that from the environment and use it in other applications, aggregate for building, for instance. Next question.
Okay, I want to get to some of the questions that have been coming in through the chat, and I'm just going to pull this one up because I've got the answer right here. Pretty much is, what was the percentage of I'm guessing detects in the EPA UCMR4, and it was actually 3 that were where they looked for PFAS UCMR3, and those the exceedances or the detections ranged between 8 and 117 different facilities. But one thing to remember is that the reporting limits were much higher than we're seeing now. So the PQLs, as we call them, are between 3 and 5 currently. At that time of the UCMR3, they were between 20 and 90 parts per trillion. So we'll see a lot more detects now than we had in that past. And let's see, I've got a question. I think, Rock, you'd probably be the best one to answer this. Is, do you believe there are concerns about the differences in the LDLs, I think the lower detection limits of the methods between method 533 and 537.1?
As a practical matter, there's, I mean, from a published method standpoint, there's probably very little differences, but again, I'm a strong proponent of isotope dilution, which is method 533 if it's followed as written. So I would expect a lot more stability and a lot more accuracy at the lower end using method 533, in my opinion.
Yeah, I would agree with that. Related to that, do you know anything about the percentage difference in air that can be expected between the two methods? I know one's isotope dilution and one's not.
In air?
I'm sorry, error. I
Oh,
didn't
error.
enunciate.
Got it.
Accent's
Okay,
coming through.
I was taken back for a minute. It's like, okay. Unfortunately, I think, again, the percent error, again, if you look at the methods side by side, the calibration, the QC requirements, they're very, very similar. So, you know, again, I think if you're talking about drinking water, the stability of the instrument that the lab is using, how it's maintained, the flutter at the low end, the instrument noise, again, I think a lot of that can be, even if it's pretty noisy, can be controlled to a significant extent if each of your target analytes has a corresponding isotope. And again, I come back to 533. If given a choice between the two methods, I would pick 533 every time. Unfortunately, you will generally always get higher numbers with method 533. And if you want to know the technical reason why, call me and I'll tell you. Thank you.
We are getting quite a few on the methods. So just one more here on the methods. Should water utilities avoid using EPA method 533 or 537.1 when analyzing unfinished drinking water supplies, source waters that are then treated and used for drinking water purposes?
I think it comes down to a matter of points of compliance. I think 1633 has all the fundamental basic chemistries as the two drinking water methods. If you're taking samples at a point of compliance, collecting a sample by 1633 may be an advantageous idea to do, as opposed to going right to your drinking water methods, which may have compliance reporting attached to it. So screening samples that are destined to be drinking water samples by 1633 is a good idea. Again, it comes back to the planning with the laboratory to be able to look at where their low calibration points are, and that can they get you with 1633 using the sensitivity you need to be able to understand, okay, if we take that same sample now, we go 533 or 537, and we're going to be over the MCL. So 1633 does have utility in that regard as sort of a screening rangefinder kind of method to use.
Thanks, Rock. Dave, maybe you can help with this one. Has anyone evaluated the impact on GAC supply and quality?
There's a lot of GAC out there. There are some big vendors, major vendors, and then there are different grades of granular activated carbon as well. And so I think there'll be an ample supply. I think if things were to get lower, you could have, it has to be an NSF 61 certified granular activated carbon, and that involves some more processing and quality control and higher specifications. But I think you can get to that specification and get to that higher quality. It's just going to cost additional cash. But I haven't seen a particular study saying that supplies of granular activated carbon will be in short supply, or there won't be enough of the media. I have not seen that.
Thank you. We have a question. Do you believe the environmental labs have the capacity to provide enough analysis of drinking water? What about in light of wastewater getting more attention and affecting downstream users? And I think this is a really good question. EPA did address this in the proposal. They identified 54 labs that have been approved to be working on the UCMR 5 program, and this is what these are the labs that they used as to verify capacity. But adding the interest in wastewater is certainly going to change that. So, Rock, do you have any additions to this?
Yes, I do. Many laboratories are bringing 1633 online. I can't tell you how many calls I've got from our industrial clients saying, I'm going to be waiting 6 weeks for data. So capacity is absolutely an issue right now. If you're getting normal turn, in little quotes, of 2-week turn for PFAS, odds are you're paying for it, and odds are it's a one-off. So capacity is definitely an issue that needs to be contended with.
Thank you. We have one on the hazard index. I think this might be the last one we might get to, but can you explain a bit more how the lab and the water system will determine if they meet the PFAS hazard index? And I don't know if it's easy to jump back to that slide with the equation on it, but basically each of the 4 compounds that will be involved in the hazard index, you take the concentration that's detected in your sample and then divide it by the reference value. So the reference values range from 9 to 2000 for PFBS. So you take each one, divide it, and then add those together. So your units are going to drop out, and then the limit is 1. EPA is in the process or has developed a tool for facilities to be using this online. So you can just plug in the numbers and go, yes, here we have it on. So you take your Gen X concentration in your sample and divide it by 10. That is the reference value here. So you just add all these up together, and that you come up with your hazard index. So it looks like we've only got a minute left, so I'm afraid we were not going to have time to get to any more questions, but we will respond to these later. We've got them all here. Thank you so much for submitting them. And I just want to thank all of our panelists today, all in our Montrose group. We all work together on PFAS daily. It's great. Thank you so much for sharing your knowledge and experience on this area and your insights into the proposed regulation. And once again, there are many different areas of Montrose that are involved in PFAS. If you have any questions for any of us or all of us, please go ahead, and we have a landing page on our website that you can get a hold of any of us and ask us any questions or ask about your project. So thank you so much for joining us today. I really appreciate it. And I'll give it back to you, Jessica.
Fantastic.
The slides will be, oh, I'm sorry. Slides will be shared too.
You're good. You're good. I was going to mention that, but yes, the slides will be shared. So I will just reiterate what Martha said. On behalf of the entire team, I just want to thank you for being on with us today. And this was such a fantastic discussion. Also, you attendees will see right now, there is a poll question up on the screen for you. Please feel free to answer that before we close up the event today. I thoroughly enjoyed listening on the background. There are quite a few people that are from exactly where I am located, so it's always nice to see some East Coasters on for these events. But again, thank you to the team at Montrose, and again, your subsidiaries. We love working with you guys, and we appreciate all of the work that you put into the event. It was great getting on and working with you yesterday through the rehearsal for today's event, and hopefully we get to do this again, because I have a suspicion that our attendees would love to hear from all of you again, especially once the regulations are in place. So have a wonderful afternoon. And if you are watching this on demand, please feel free to submit questions, because any questions that come in on demand will be directly sent to the team at Montrose. So once again, thank you all. And we're going to conclude the webinar, and I hope everybody has a wonderful rest of the day.
Thank you, everyone.
Thank you.
Thank
Thank you.
Thank you all.